Good evening and welcome to this evening's video. I'm going to be talking this evening about the methodology that we use to determine specific elevations at specific points along a line. The purpose of this video is the most common example of that, which is to determine the elevation on a curb line in a parking lot or what have you, where the elevation is a specific number. In other words, if you're drawing a map or even just doing calculations in the field, there are going to be times where you're going to need to determine what point along a given line, assuming that the line is on a slope. If it's flat, obviously this doesn't apply. What point that a line or a proposed curb line, in the example we're getting ready to do, is at a given elevation. In the real world, we use that to determine the elevation of the points we use to stake out a curb or even a pipe under certain circumstances. There are going to be numerous occasions where you have to do this process. Anyway, without further ado, we're going to get into it. Basically what we've got here is a very simple process, again, of interpolation. In our contour video, we discussed interpolation of contours, and this is very much the same thing. As a matter of fact, we're going to use contours as an example in our first attempt here. And like I said, without further ado, here we go. Once again, I remind you that all of these examples are made up on the fly, so it's going to take me a minute to do some calculations. There's always the possibility we'll come up with a weird answer, and we'll have to back figure that and solve our problem. But that's what we're all about. We're all about solving problems. So, here's our example. We're going to give you a bit of a sketch. Imagine a parking lot that looks kind of like this, part of a parking lot. Here's your curb line. You know the elevation here, and you know the elevation here. Let's just say, for the purposes of our example, the elevation here is 247 feet. And let's say the elevation here is 244.4. There we go. Now, those are the elevations of the point. In our example, let's say there's, I don't know, 7 parking spaces in there. Let's say that they are about, we'll make it easy, we'll say 70 feet apart, horizontally. So you have a 70-foot horizontal distance, and you know the elevation here, and you know the elevation here. Well, step one, let's figure the change of elevation. 247 minus 244.4 gives us a difference of 2.6 feet. So, our delta elevation is 2.6, and our horizontal distance is 70 feet. That means our rate of change, you got to start thinking of this in terms of a rate of change. You can use percent if you prefer. But here, we had a little bit of a technical mishap there. Had a light fall over. We're going to make a temporary cut. Excuse the jump cut. Let me fix my problem. We'll pick up where we left off. Okay, I'm back. Sorry for the mishap. Had one of my lights fall over here, so had a little bit of a problem. Now, back to the math. We have a delta elevation of 2.6 feet in a horizontal distance of 70 feet. That means we got our rate of change, is going to be 2.6 divided by 70. Do our math right quick, fire up the calculator. I'm not going to try to do that one by hand. 2.6 divided by 70 gets you, in round numbers, 0.037 feet per foot. Now, here's where the conceptual difficulty comes for a lot of people. Don't allow yourself, if you're struggling with this, don't allow yourself to sink into the swamp of just the numbers. The number doesn't matter. It could be any number. You've got to understand the concept. What we're dealing with here is 0.037 feet per foot. What that means is for every foot you go horizontal, you go up, or you go down, depending on which direction you're going on the hill or on the slope, 0.37 feet. So you go over a foot, you go down 0.37. You go over 2 feet, you go down, what would it be? It'd be 0.074. So you're just constantly going down or up, again, depending on which end you start at the rate. Now, what that means is, if you know how much elevation change you have in a given distance, and you know how far you got to go, you can compute your total elevation change. It's 0.037 feet per foot here in our example. If you go 10 feet, it'll be 10 times that. It'll be 0.37 feet, by that much, okay? A little over a third of a foot, or whatever it would be, 3/8 of a foot, something like that. Anyway, that's one way to do it, but for the purposes of our example, we're going to figure it the opposite way. Here, we don't know how far we're going to go up whatever distance we calculate. We know how much our elevation needs to change, which means that to get to a certain value, instead of multiplying the horizontal distance times the rate of change, you take the total change in elevation and divide by the rate of change. So, here's our example. We're going to start at the high end and work our way down. It'd work just as legitimately to go the other way. But we got an even number up here, so we're going to make it easy on ourselves. Well, we want to go, our next even number down will be 246. So that's a change of elevation of 1 foot. So like I said earlier, our horizontal distance, excuse me, let me erase that. I'm not going to skip a step here. What I was talking about earlier, our delta elevation is going to equal the horizontal distance times the rate of change, which I'll abbreviate as ROC, just to be silly about it a little bit, keep it a little lighthearted. Well, if delta elevation is HD times the rate of change, that works great if you know the horizontal distance and the rate of change. In this case, we know the rate of change, we just calculated it. This is a straight line, so the rate of change is going to be the same all the way along it. We can figure the delta elevation. So if delta elevation is HD times rate of change, that means HD is going to equal delta elevation over rate of change. Well, in this case, we want to go from 247 to 246. So our HD is going to equal 1, which is our change of elevation, 1 foot divided by 0.037 feet per foot. That's going to give us, get out the old calculator here, make it quick, 1.037 divided by 27 feet. 27.03 technically. We're just going to say 27 feet. 27 feet. We're going to round. All right. Well, I'm going to kind of halfway scale here along this. If this is 70 feet, 27 feet is going to be a little over a third of it, right? A little over a third of it. So let's divide that by 3. We'll say 27 feet is right here. 27 feet. So that's 247. That makes this 246. Well, guess what? The change of elevation from 246 to 245, which is the next whole number down, is also going to be 27 feet, right? So we go another 27 feet. And that gets us to 245. Now, if we calculated right and we scaled right, we're kind of done. But like so much else in this business, you don't want to just run the numbers and let it slide. You want to check. You want to check. So we've calculated a horizontal distance to here and a horizontal distance to here. If we do the math to determine what this horizontal distance should be, and it kind of matches what we've got up here on the board, then we know we did it right. If it comes up with some crazy number, we know we did it wrong. So we're going to check ourselves. Again, we're going to use the same formula, but here our delta elevation is not 1 foot, it's 0.6 feet, because we're going from 245 to 244.4. So HD, I'm switching to blue here, is going to be 0.6 divided by 0.037. Whip out the old calculator, get 16.2 feet. Okay? Well, 16.2. Well, we didn't really scale it like you would if you had a, a measuring device, a scale, and a piece of paper. But we did kind of eyeball it, and we can still add up the numbers. 27 and 27 is what? 54. 54 and 16.2 is 70.2. So we got a little bit of error, 0.2 feet. In the grand scheme of things, you're building a concrete curb on a parking lot. That is close enough for what you're doing. If we were to redo this and carry this out, all of the digits, because it's really not 0.037, it was 0.03712 something, I think. If you carried out all of the digits, this would not have been 27 feet. We rounded. It gets back to the whole concept of good enough for what it's for. But that is one good example of how to interpolate where a given point elevation is along a curb. Now in a minute I'm going to do another video. We're going to do basically the same thing, but this time instead of trying to get a whole elevation like you would if you were trying to draw contours in there, we're going to try to get specific elevations like you would if you were trying to compute the elevation of the curb for construction. Anyway, I hope you understand what we just did. I'll do another one, and we'll try to work our way through it. The important thing here is, just like always, take your time, draw a picture, think about it before you start punching the numbers. Understand the process before you start punching numbers. Then you're probably going to come up with a good answer. Just start punching numbers randomly, you're liable to come up with some crazy stuff. If that number turned out to be 46.2, we know we would have screwed up. Turns out we did good enough. Anyway, I hope you enjoyed the video. I wish you all a pleasant evening. Thank you.